So our first of three is Masahito Yamazaki. The TT bar and root TT bar deformations. Very different.
Okay, great, thank you. Well, so like other speakers, first I'd like to thank the organizers for coming invitation. I came all the way from Japan, so I'm a little bit jet lagged, I'm afraid. So my responses might be a little bit too slow, but it's definitely worth it for me. Especially, I mean, I know this conference has been going on, and I missed some previous editions of the workshop, so I'm very glad that I could make it this particular time. And I also say that I'm very also pleased to be here at Stockholm in particular. I've been here, and in fact I went up and have enjoyed a nice view, and so it's a fantastic experience despite being jet lagged. And well, so and in fact I should also thank Scientifically for this event because I thought that I should talk about something which is closely related with the topic of this conference, and integrability. And so I thought that I should talk about some topic, and then I thought about what I should talk about. And then opened my overlay, and there was a nice project which was supposed to have been done many years ago. So not coincidentally, I have taken this opportunity. I spent the last couple of days working very hard to finish up a paper. So which will appear, I mean, if the archive doesn't mess up things, it will appear tomorrow morning here. And in collaboration with Roberto Tateo and okay, it's here, but it's a little bit hard to see, but with Junichi Sakamoto and myself. So it's a paper to, and my presentation itself is right after the lunch, so I don't have too many equations, but if you want to check all the equations, etc., please wait a couple of hours, and then you can download everything. And then, in fact, I want to discuss. I know that there are many experts, in fact, who are much more knowledgeable about some various different aspects. So we can probably talk about it even tomorrow. And okay, so let's start with the story. So first of all, I think well, we should start with what is the motivation. And well, sometimes you have to motivate this and that, but in this class, you don't need that much of a justification. And clearly, the topic is integrable quantum field theory in 2 dimensions. And so that's and then I want to deform it while preserving integrability. So that's, of course, the topic of integrabilities and deformations. And well, the particular deformations I'm going to discuss are like TT bar and the loop TT bar. And that's, of course, a very fascinating topic. Again, I don't need to introduce you. And you might even hear some other talks. And there is a very curious deformation. Even physically, like a TT bar, for example, people discuss going up in the RT flow, non-locality, or holography, everything. And then even a connection to integrability, of course, which was the more original motivation. And then people discuss, they don't stop there. There are also square root TT bar, and then sometimes it's integrable, etc. So that's a very rich topic. And of course, as I said, some people in the audience have already worked on that and more of an expert than me. And but at least I like to understand things somewhat in my own way, as always. And so one of the ways I do that is to go through this 4-dimensional Chern-Simons theory, so-called. There was a related talk already, and so that's a framework where you start with the 4-dimensional theory, coupled with the 2-dimensional defects. And as is often the case in string theory, and always for the higher dimensions, some of those things are geometrized and have a clear understanding. And then, of course, the question is, can you deform it? Then can you incorporate the deformations, like the TT bar deformations, in these discussions? And that's the question I'm going to address. And I should say that I'm not going to resolve everything, actually. So there are some unsatisfactory aspects. But nevertheless, I think I make some progress. So that's what I'm going to report. Okay, so let's see. Let me have a recap well, of the 4D Chern-Simons, and I just have 2 slides or so because some of them might have heard, and in fact that was also covered in previous versions of the event. But just have it doesn't bother you too much to have just 2 slides or so on it, because I'm going to use some aspect of that in the following discussion. And of course, this is a 4D channel simultaneous action. It's and the particular thing is that it's defined R2, where you're going to have the integrable field theory. That's if you're a 2D person, that's where you live. And but then of course the transverse direction, which is the spectral curve, and then there's this omega in the action, which is the holomorphic manifold. And that's going to play an important role. I'm going to talk about the poles and zeros and etc. So omega is play a very crucial role, and it depends on the holomorphic coordinate on P1. So things are holomorphic in that direction, which is not surprising because we have a spectral curve, spectral parameter, which is a complex parameter. So I don't see, but in my talk, essentially C is just a P1 with a bunch of poles. And then the connection to integrable field theory comes in. Well, this is a fully channel itself a really trivial theory, but you can include a defect at the various different points. And in these fields, you are 2 dimensions, and but you can have multiple defects. And then, so that's a whole coupled 2D, 4D theory, but you can integrate the theory along the 2 dimensions. If you like, you can try to make the C direction P1 very, very small. And then you get some 2-dimensional integrable field theory. Well, of course, this is just a field theory, but I call it integrable because actually in 4 dimensions, there's an equation of motion, which says that F equals to 0. Of course, this is the flat connection equation. In fact, omega wedge F equals to 0. That's the equation of motion you get. And but in some gauge or so, that immediately boils down to the Laplace equation down in 2 dimensions in some gauge. So the nice thing is that it's completely automatic, at least in this construction, to have a classical Laplace equation. You can talk about the quantum integrability, which I don't do too much, but at least you can discuss the classical integrability. Of course, if you just have a specific field theory, it's always tricky to try to find integrable structure in this Laplace, but it's automatic in this construction. Now, and then I have just one more slide, and then what type of things, because related is what I'm going to discuss next. So, for example, there are various different defects you can consider, and this is one of my favorite examples. So, there are 2-dimensional defects, and there are a variety of defects, but suppose that you have a free fermion defect, chiral, antichiral, and here you have a chiral and antichiral defects, which are themselves just a free fermions, no interaction whatsoever. So they are on their own, but you can let them talk with each other through the exchange of the 4-dimensional gauge field in the bulk. And then through the 4-dimensional gauge fields, they begin to talk with each other. So this is actually like a brainwire scenario, and then this is our universe and the other universe. And then, so if you integrate out the gauge field, there's a propagator gauge field, and then there's a coupling to the current, which is type psi, and it generates the 4-Fermi interaction, which is how you get this interactions. So that's an example. Okay, so this is a recap. And I talked about this because, in fact, by looking at it, you might be tempted to think about the TT bar deformation actually this way. Because, you see, there is this JJ bar. And now, why don't you replace it by T? so that was actually how, sorry, let's see. So in fact, I can even come here. So that was actually how the original attempt in this TT bar deformation, the 4D Chan-Simons theory. So, well, the idea is very similar. I have essentially the same picture. And then I just replace T by A. But of course, A should be like more like a gravity. And then the original proposal, interesting paper of Victor Phi in 2022. I know that, anyway, so that's in that paper, they say that, okay, so instead of talking about the compact group Chan-Simons, why don't you consider SL2 Chan-Simons? It's a non-compact group. And roughly speaking, it's like a 3D Chan-Simons gravity. So, and then you can integrate out. And then again, instead of JJ bar, you have a TD bar. And so that's, that gives a realization of TT bar deformation. So that's the paper by Victor Phi, which is an interesting paper. And well, except that I certainly have a similar idea, which is not a coincidence because Kevin Cosell was interested in that. And then in fact, I know that I also met him long ago. And then but only after many years, he also wrote up this paper, etc. So it's an interesting idea. It's a very tempting idea to realize TT bar deformation this way. And however, I didn't, at least myself, I didn't write up this way because I mean, despite the fact that this is very tempting, I have some questions about this type of logic, of how to understand the TT bar deformation. And I'm not going to tell you everything. Maybe some people in the audience can come up with some more complaints. But one of the reasons is that, first of all, the TT bar deformations it deforms the Lagrangian by parameter lambda. And on the right-hand side, you have a stress tensor. But the stress tensor of the theory, lambda, not the theory of the stress tensor of the original theory. So in other words, this is a non-trivial deformation, non-linear deformation in lambda. So if you look at the previous construction, there is no such thing, TT bar. So it's correctly, the authors correctly realize that this is only linear order in lambda. Of course, then you can ask the question how to incorporate the higher orders of lambda. It's not completely clear to me, and to some extent, if you really want to reproduce this TT bar deformations, I mean, it's not like you have to think about it. It should come automatically to some extent. And also another question is that, thanks to the work by other people, we now know that the TT bar, at least in some specific class of series, is not the only deformation. There is a square root TT bar. Maybe there are more crazy deformations, which we don't know. So there could be many other deformations. So it's tempting to have TT bar this way, but of course you have to have what about square root TT bar this way or that way. Maybe you can try to imitate that, but it becomes more non-trivial because now we square root. So and then as I said, there might be other deformations which goes beyond that. So then in fact the point is that at least if you want to try to reproduce composite transform, at least the ultimate goal is not to take the literature TT bar translate, square root TT bar translate, but if you go the other way around, so just forget about everything in the literature, but try to classify this. That's at least the ultimate goal. And as I said, I'm not going to do that, unfortunately. So I'm not going to tell you that much of a new results in that respect, but at least that should be the motivation. And then so for that purpose, it will be unsatisfactory. And also maybe the last point is that so in the previous discussion, so there was a production to SL2 Chern-Simons and that's 3D gravity, which is of course great. But of course the theory is 4 dimensions, 2 plus 2. And the theory is not horomorphic, it's completely topological. Some direction horomorphic is not a topological theory. So we should actually consider the 4-dimensional gravity, which is not completely topological. So what does it mean to talk about the 3D gravity here and things like that? So there are a lot of questions of this type, which ask us, like, could there be other description of this type of TT bar deformation inside the 4-dimensional Chern-Simons theory? So that was the question I want to address. And as I have told you, it's not like I have a good answer, but at least we have a different approach for thinking about this problem. Of course, there are some similarities, but in practice, it's very, very different. Now, how to think about it? Well, first of all, let's first go back a little bit. So the story I had was that I have 2-dimensional integral of quantum field theory, which comes from 4-dimensional theory, 4-dimensional Chern-Simons theory with detail. Now, sometimes people discuss the dimension reduction of 60 theory, 60 horomorphic Chern-Simons, etc. So 60, 5D, there are a lot of theories. Now, if you try to get the string theory, you immediately find that these are so-called open sectors of the theory. So, you know, string theory has open string, cross string, can engage in gravity, and then this 4-dimensional Chern-Simons theory is open sector. Now, which means that we should couple to some version of the gravity. So they are not the full gravity. It's a kind of topological, partial topological twisted version of gravity. And in fact, people have an idea. For example, the 60 horomorphic Chern-Simons, it's supposed to couple to something called a BCOB theory, or Kodaira-Spencer theory of gravity, which describes the complex structure deformation. So some of you might be familiar with the Calabial discussions and complex structure deformation, E-model, and that's this Kodaira-Spencer gravity. And now, and then of course you can go back to 4 dimensions, and then you have to tune T duality, and it's some hybrid of the A model and B model. So that's what you may expect as some 4-dimensional theory of gravity. And okay, so you can write down the Lagrange, etc., but the details are not terribly important. But the point is that you have some gravity degrees of freedom. And the idea is that this is a very, very general comment, but you have some open sector. And then the closed string degrees of freedom, it looks like a kind of like a background. So you can actually change the background. And then from the viewpoint of the open sector, it looks like a deformation. So some degrees of freedom come from this closed sector, yes.
Why do you expect the scalar gravity to be 4-dimensional?
Check.
Why do you expect that in closed sector this 4D tower gravity is actually 4D theory?
Well, let's see. So here it's you start with the 60. But in other words, this four-dimensional chance-level series is partially topological, partly holomorphic, and in fact, it's actually like a hybrid of A model and B model. So I should have also that should obviously be the case in the gravity. So partly Kähler deformation, partly complex structure deformations, and then Kähler gravity is for the A model, and Collider spacer gravity is B model. So you actually need some hybrid of that.
Shouldn't it still be 6D theory since it's a closed sector?
So, sorry.
Shouldn't it still be 6-dimensional theory?
Well,
it's just duality in closed.
Well, yeah. Well, let's see. So this is the field theory version of the T-duality, so-called, and so it's actually like a more like a dimensional reduction in a sense. And well, in other words, this is a four-dimensional theory. So I should couple the four-dimensional gravity in itself. And yeah, so if you know the string theory T-duality, that's of course that's a slightly different context. But yeah, but this is called the field theory T-duality. But if you like, you can actually think of it as just a dimensional reduction. So you start with the 60 theory. So here, on both sides, open close, you just dimensionally reduce from 40 to 60 to 40. Yeah, but anyway, actually the details of this theory doesn't matter because I'm not actually, so my presentation is insufficient in the sense that I'm not actually going to give a detailed analysis of this theory, and I'm going to circumnavigate that a little bit. But it's starting to talk about this, but because at least in principle, this should be the logic, right? So, and okay, but let's keep setting aside the details. What type of structures? I'm not going to analyze the detail, give a detailed analysis of the theory, but just imagine what type of things that happen, right? So, and of course, we have the open string sector coupled with the gravity. And then what are we going to do? Well, of course, it's a coupled system. But typically, you first solve for the gravity equation function. So you first have the gravity, schematic of G, and then there is some extra degrees of gauge field and defect degrees of freedom feature denoted phi, open sector and closed sector. And on the closed sector, you should first solve the equation of motion for this metric G. And then, of course, the closed sector and open sector coupled with each other. So when you solve for the solutions do depend on the open sector, which is denoted by phi. So you first solve for the gravity, and then you get the on-shell gravity background, which depends on this phi. Right, so that's what you would expect. And then what you should do is that you should just analyze, now the background is fixed. You should just analyze the theory on that background. And in fact, it turns out that, well, of course, this is a very general comment, but in the case of 4D chance-simons, the choice of this background, you can actually transform, well, kind of eliminate that almost, well, not completely, but quite a bit by some coordinate transformation. So, so that's one of the logic. But of course, the point is that here, it depends on phi. The metric depends on phi. So what you expect is, after all, what you should do is some coordinate transformation, which depends on the phi.
What is phi?
Oh, sorry, phi is the fields inside this four-dimensional chance-simon coupled with defect. So in practice, you can think about the defect degrees of freedom. So, or it's like open degrees of freedom, yes. And so in other words, so what you should do from this argument, you expect, I mean, this is a very, very general argument, but what you expect is that you should do some sort of a coordinate transformation, etc., which depends on the field phi, which is the degrees of freedom. So you might call it, sometimes people call it a dynamical coordinate transformation or field-dependent coordinate transformation, and that's what you expect should be something happening here.
Sorry, can I just ask, why does it have to be a field-dependent diffeomorphism as opposed to just a field-dependent metric that doesn't come from a diffeomorphism?
Well, let's see. I mean, yeah. So in general, it's just a metric. But so indeed, if you just try to solve everything, it's everything depends on the full data of the metric. But here in this case, there is essentially the theory is holomorphic, for example. So well, there's a little bit of asterisk. So what I'm saying is not completely actually correct, but more or less it's a theory of holomorphics. So it should depend only on the holomorphic structure. So the complex structure deformation, if you do complex structure deformation with that, you can that you should be able to represent that, and that's what's going to happen. So yes, so that's what you would morally expect. Any other questions? Yeah, so this is like a very broad logic, and it turns out that if you stare at the literature of the TT bar, well, it looks like there is something very, very similar in the literature. So if you look at the literature, there's a discussion of TT bar deformation, and then people discuss TT bar deformation from different viewpoints, coupling to JT gravity, which also is tempting to compare with this, but also allows some this dynamical field-dependent coordinate transformation. That's discussed. And again, it's not completely clear how general that is, etc. But for cluster examples, people discuss. For example, in sign Bowling, some of the original papers. And so it's actually tempting to identify those type of field-dependent transformations as the incarnation of this philosophy. Of course, if you solve the actual gravity equation, most of that should be the consequence. But for the moment, I want to be a little bit more practical and use this field-dependent coordinate transformation and use it as a trick to introduce the TT bar deformation. But not in the purely 2 dimensions, which of course these people did, but also up in the 4 dimensions. So that's going to be the story. And in order to do that, of course, I have to put the 4D 2D theory on a colored background. And also for which theory we're going to discuss. In practice, we chose to discuss something called the degenerate E model of Prinzek, and which includes a variety of models like a principal color model, for example, and which some of which I'm going to come to afterwards. So, okay, so first let me introduce this dynamical coordinate transformation, starting with a TD bar. And you can just look at the literature. And this is, yeah, I mean, you can ask where it to get, but so far just take it from the literature. So this is some coordinate transformation, right, from coordinates. But of course, the point is that there's a T here. And so that's a field-dependent coordinate transformation. So, of course, this was discussed on a particular class of theories, but since this is written in a general way, so I'm tempted to take it and then try to apply it to more general context than the original one. And there's some nice thing about this coordinate transformation. In fact, it's related to the fact that this TT bar deformation is actually nonlinear, which was one of the complaints I had about the previous approaches. And in fact, it's a non-trivial algebra, but it turns out that if you do this coordinate transformation from the x plus x minus 2 prime variables, and then you can use this. So this is a lambda deformed action. And it turns out that if you use this deformation, you can essentially linearize this transformation, which is a very clever coordinate transformation.
Are the differentials exact?
The differential is exact. Well, there's a few fields inside the T. So if you try to take a derivative, etc., you get a derivative of the field, which is, in fact, that will become crucial in some of the.
So the primed ones are exact as well.
Sorry, primes.
The left ones.
Yes, left ones. Yeah, I mean, if you take a derivative of them, yeah. So I think it's so this is just a local coordinate, but it's a field-dependent coordinate transformation. So it's yeah. So
It's correct, right? Because of the conservation stress.
Oh yeah. Sorry. Oh, that's what I asked. Yeah. It is. Oh, okay. Yeah. That's what I asked. Thank you. Yes. So yeah. Okay. So things are reasonably consistent. So and yeah. So it's a nice transformation, and in fact, to kind of linearize it, and in fact, so you can see that this coordinate transformation has something. It's a kind of like it's a flip of the coin of having this determinant. So the things are kind of entangled together. So that's so it's important to consider kind of both this coordinate transformation as well as this determinant, and so that's how the structure appears. Yes.
Sorry, if you place that theory in a cylinder, it's not linear anymore. It's still non-linear because all the dependent on lambda will be picked up by the radius of the cylinder. So that's only for a flat space.
Yeah. Yes.
Because this is a common misconfusion that
Okay,
people say it's linear, but it's not linear.
Yeah.
Just
Okay.
hidden.
I see. Thank you. Yes. Thank you. And yeah. So okay. So then so this is the coordinate transformation, and you can try to use it, right? So the Lux equation. So you can start with the Lux of the original theory, and then do this coordinate transformation. And you can write the different components of the Lux in the different coordinates, for example. And then so let's see. So this is like a reasonably like a simple looking operation, but of course it depends on the fields, and that depends on the fields. Okay, for fields are localized at the defects of the curve. So there are 2-dimensional defects in 4 dimensions, and then because of that, it's non-trivial at the defects. And so it's actually non-trivial what happens. I just introduced the coordinate transformation in a sense out of nowhere, out of the previous literature. Of course, no guarantee whatsoever in general yet. Like it preserved any good structure. But at least what I said so far is that away from the defect, essentially the folding transform is homomorphic. So if you do the coordinate transformation, you can just undo it essentially. But of course, the question is what will happen, and it may depend on the specific model. Ideally, there is a very general argument, but in this talk, I'm going to discuss that for some model called the degenerate E model. So let's see. So let me try to introduce this degenerate E model, which was discussed especially in the 4D transform context, but the series papers by Benoit. That's how I learned it. And in fact, the formalism itself is rather complicated. So I try to, in this presentation, I try to squeeze it. Maybe a little bit too much. So some aspects is a little bit precise, but but at least again you can download the paper. So let's see. So first, okay. So what is the starting point in the four-dimensional Chern-Simons theory? So again, we have a spectral curve in this one form, and now I consider the so-called disordered defect, which are the singularities of this omega. And then so you have a set of poles and zeros, and the poles and zeros are obviously both important. They're even related to residue theorems and things like that. But again, in this talk, I'll actually almost disregard the zeros. Zeros are extremely important, but I try to hide the zeros in this talk, and I just highlight the poles. Okay, and then there are some poles at some points, and that's up to some order. And then okay, so you want to say what happens if you have the poles? Now, if you have the poles in the omega, the four-dimensional Chern-Simons actions omega with Chern-Simons. And now omega sitting in front has a divergence. And that means that when you consider the perturbation around classical solution, etc., you have to consider higher orders of expansion around the gauge. So basically, omega with gauge field dA, A with dA. And so when you do this perturbation, then you have to make sure that the action is essentially finite. So if you have a pole in this one form, then what you should do is to consider not just gauge field, not just as an element of E algebra, which is tangent to this D group, but up to some order in the Taylor expansion at that point. So that's sometimes you can formulate it to some jet bundles, etc. But the more practically, just say that instead of the real algebra, you just have a form of variables and then go to take some higher orders and expand it. So that's people sometimes call the Taki algebra, etc. And at each point in this each point pole of the one form, you have to do that. So that's like a boundary condition, degrees of freedom, and that's we denote the real algebra we denote by D. So that's for the defect D algebra. And it has a nice bilinear form because it's induced from the original real algebra, etc., etc. And so that's like what are the degrees of freedom? Now, of course, this is just well, you have to talk about the variations of action and put the boundary condition, right? So I just specify the degrees of freedom, and then you have to impose the boundary conditions. And roughly speaking, as is always the case in the quantization, you have to take a Lagrangian subalgebra out of it. I just wrote it somewhat more formally, and then you have to make sure that the action is zero. So the tricky part is that this is d omega, which is, so this comes from the variation of actions. And in most of the points, d omega is zero because omega locally can be written as a derivative something. But at the singular point, it hits poles and then the zero function coming up. So you have to be careful. So that's a little bit of a more technical explanation. But in the end, well, you should choose the maximum isotropic subalgebra where so there was this bilinear form, but the bilinear form should be zero on this subalgebra K. And then we take a maximally largest one inside it. So that's this K. So you have this defect algebra and then K inside it. That's the defining date of the theory. Now, and then once it does specify the boundary conditions. Now, once you specify the boundary conditions, you have to integrate out the theory along the curve C to get this theory. And then there is a moduli space kind of like that. And then the moduli space will become, we look like a fuse of this theory. Now, what are the degrees of freedom? Well, again, everything localizes at the point of the poles. And then so at the point of the poles, so this is the correction of poles. And then it takes values in the defect group. So there is some localized degrees of freedom, which are denoted by H. So, and it turns out that, sorry, let's see. Oh, okay, so this is, yeah, okay, so I think I can come here. So the degrees of freedom is takes values in this this H is localized at the poles of the one form, takes values in D. Now, because of the boundary condition, you actually have to take a coset, D over K. And now, in addition to that, we have a gauge transformation. So this whatever these fields, etc., this comes from the gauge field. And the gauge field, of course, has the gauge transformation. And now we have a lot of defect fields, so which is like the value of the gauge field at different points. But of course, there's the overall gauge transformation, which you have to model out. So you have to consider some concepts. And then lo and behold, this type of structure was discussed before in this the degenerate E model of Primtech and Severa. So so that's the formalism I'm using. And in particular, what's nice is that once you specify this field H, and then you can also write down the Lux operator. And there is this equation which I don't actually even explain. Because to properly explain it takes some time. But it's a reasonably simple expression, which is a little bit abstract expression. So I have to spend like extra slides to explain this properly. So I'm not going to do that. But the point is that there is a nice concept, and then you can write down the lots, everything explicitly, which I borrowed from paper by Benoit. So okay, so this is the setup, and this degenerate E model. So it's called a degenerate because there is a quotient of F, which is like a gauge transformation. And it describes an interesting, you can describe an interesting variant of the T duality here. And also, it actually includes, for example, Yamazaki deformations and lambda deformations on some principal color model type things, again, discussed by Benoit and others. So this itself describes some, is a good structural theory. So in any case, the point is that you can start with the Hody transform with some one form with a high order pose, and then you can generate this degenerate E model. Now the question is that so you can now so that's the theory, and then now we can try to come back to the discussion of the TT bar deformations as introduced by this dynamical coordinate transformation. So let's see. So that was many slides ago. So people probably don't even remember, but at least there's this nice, beautiful coordinate transformation. So and now and then now also have the degenerate E model as a theory before the deformation. So now the strategy is very clear. So we already have the model, and we just try to apply this type of coordinate transformation, whatever it is, which depends on the stress tensor. Now you can do that.
Can I come back to this point, if
Yes.
you don't mind? We sort of agreed that this is an exact differential if you use the conservation of the energy momentum tensor.
Okay.
But that's on cell. And you're doing it the transformation of cell.
Well,
The action. So
It actually doesn't matter. Doesn't matter. The action is still fine. The deformation.
Okay.
do you use the conservation?
No, you don't need to use it.
Okay.
It doesn't matter.
okay.
There's a paper I can point to you exactly where they.
Okay, sounds great. Well, this is an excellent audience. That's exactly what I'm looking for. Well, that's amazing. So then let's go and yeah. So just apply this coordinate transformation, right? So and then in fact, but like of course, if the coordinate transformation is not Q dependent, well, we know what it is, and then there's some extra degrees of freedom on the boundary, etc. But of course, that is already taken care of when we discuss the theory itself, right? So, but of course, because the coordinate transformation is Q dependent, there is extra contribution which worries us, right? So, and then of course, it might spoil up the story completely, and in fact, it may be in general. But and in fact, there's this particular term which I wrote schematically. So there are a lot of there's a projector, etc. At least there is this H. H is the original field. So fields of this degenerate E model, and there's a derivative, and so there's defect pairing, and then there is also this Lux operator, Lux connection which I wrote before, and this J star proves back that Lux connection onto the defect, etc., etc. But again, the details doesn't matter too much. Now, if you look at this equation, here is a nice combination, which is the Frat connection equation. Yes, thank you. So Frat connection equation. So this is a nice combination, which is good for classical integrability, right? So, but there is an annoying term, which is here, and then there is a gamma star is some metric, but of course it depends on the fields. So there is a non-trivial variation, which might spoil up the story completely. And then in fact, I don't know the general story, but at least, for example, in the specific case we discussed, we can do the algebra somewhere in the appendix, that this term is actually the variation of the determinant of t. And you can show that. And then now that it's the case, it's very good because this is the unwanted term, but you can cancel this unwanted term by incorporating this minus of this same contribution, its opposite sign, into the action. So if you incorporate this, so this is a dynamical coordinate transformation, which itself in itself spoils the story. But the point that there's a way to remedy that by adding a specific term in the Lagrange, which is the determinant lambda, which is this TT bar deformation.
Sorry, what is this gamma?
Sorry, what is this gamma? Oh, gamma is the matrix, yes. And,
In 40?
no, in 2 dimensions, yes, in 2 dimensions. So, so we do that, yeah. So in other words, we do this coordinate transformation. So, oh, sorry, it's a little bit far, and I just like on the components here. And yeah, so
Non-trivial 2D metric.
yeah, non-trivial 2D metric is depends on the stress tensor, yes, and everything. So it depends on the stress tensor. So when you do this thing, so you have to. It depends on the stress tensor, but in the end, the statement it becomes a variation of this determinant of t. So that's yeah. So indeed, I didn't explain the notation properly, but yes, please wait again a little bit. And then, so that's how things work. So indeed, so that's do the dynamical coordinate transformation plus the deformation action, which preserves the structure. Now, I don't necessarily, so a lot of the computation was done by Sakamoto-san, for example, and then I don't necessarily understand the inner working of why this works. And it's actually very interesting to see how general this is. Maybe some of you are so familiar with the topic, so you can see it. But I don't know, but at least in this case, it's true. But you can try to repeat the exercise, go to DORAS or schema surfaces or with different defects and what happens. And I have no idea, but at least in this case, in this particular case, that seems to be true. And so this is the discussion for the TT bar deformation. And interestingly, you can try to do the similar things for root TT bar deformation. Again, at least for some specific crossover series, people realize it from the dynamical coordinate transformation, which is again already a non-trivial thing to do in 2 dimensions. But once somebody has done it, I can just take it and then try to repeat the exercise, but now for more general crossover series and see what happens. And then, of course, some other people know that TT bar and can be combined with a square TT bar with the 2 parameters, and they support commute, and you can even try to incorporate that into the discussions, etc., etc. So that's the state of the art for our discussion. Now, one interesting comment is that, so now there's a dynamical coordinate transformation which I introduced, and then so it's a transformation of the 2D metric. Now, even the coordinate transformation of 2D metric, you can of course divide that into the complex structure deformation, so the Bertrami differential part, and the overall part, the Taylor deformation, the Dilaton part. And at least despite some of the things I said previously, at least if you just do the decompositions, the generalized coordinate, dynamical coordinate transformation involves actually both complex and Taylor deformations. Despite some of the things I said before, it's a state of the art. So I don't necessarily claim to understand why this is the case again, but that's the state of the art. So whatever the gravity degrees of freedom is, it's not completely complex, for example. So it should involve both. That seems to be the story. So let's see. So that's our discussion. So what we discussed today is to describe our favorite TT bar, TT bar, and the square root TT bar deformations. And I presented, first of all, the general argument that some of these deformations should be understood from the deformation coming from the gravity degrees of freedom. Of course, I should emphasize that not everything comes from gravity. For example, even inside the Bodichon assignments, etc. For example, let's take some principal color model, there's a coupling constant, etc. And this coupling constant, you don't need a gravity. For example, there are some punctures and the distance in the punctures, and these are the parameters, let's say. So you can, for some purposes, you can stay in open sector, and then you can insert the deformation of the theory. And that's really this RG flow, etc. But some other deformations feature like a TT bar deformations, and I think a lot of people have the feeling that it's a different type of deformations. And indeed, string theoretically, they come from the closed sector degrees of freedom. And then the incarnation of that is that we should do some coordinate transformation, but on the field dependent one. In particular, it depends on the stress tensor. And then once you understand that, you can try to apply it, and then And indeed, it does generate that STD bar deformation as expected. Now, of course, so if this works, to some extent, there is a Lax equation, so at least classically, it's automatically guaranteed by definition that we have a classical integrability of the model. But now, my understanding is that whether, for example, square root TT bar, for example, whether it preserves the integrability in general, that's the open question. And you can see the parts, some aspect of that. For example, when we discussed this thing, for example, something happens, and so if at least in my way of formulating whether this type of thing happens or not is one incarnation of whether classical integrability persists or not. Now, whether that's how general that holds or not, I don't actually know. But of course, it's a kind of tempting to consider to speculate that maybe this type of structure is much more general. And but if that's the case, there should be some underlying explanation of why this is happening. And so that's what I wanted to say. But partly because I started to talk by mentioning the previous work, so I could try to get a grade on how far I achieved. For example, I definitely have a nonlinear so-called deformation. And that's definitely true. Like a dynamical coordinate transformation actually implement that is extremely crucial. So it's not like you get a linear order and then try to work hard to get it, but it's kind of automatic, as it should be, I guess. Now, and then of course the other deformation they incorporate the square root TT bar. And so this is actually not completely satisfactory, but so the hope is that if you analyze the gravity, so this is related to this, but at least if you analyze the gravity in more detail, we should also derive from first principle the dynamical coordinate transformation. So that's open questions. But at least for some class of series, like the degenerate D models, I could generalize the construction. So the construction is reasonably general. And so that's the state of the art. So, and in general, of course, the ultimate question is that can we use this framework to classify all the possible integrable deformations of a given integral quantum field theory? And at least in this framework, the key is to study gravity. And that's my main message. Thank you.
So we have some questions, and the first one is.
So this TT bar deformation, you can think of it as a twist of the boundary condition of the fields using momentum and energy. But there are simpler, in a sense, twists that you can do. For instance, if you have some symmetries, I mean, one symmetry like representative twist in single model. What are is it known how to interpret such like representative twists in the four-dimensional language?
Yeah, that's all. Well, in fact, I was asked the same question in the day one, but of this conference, and yeah, I mean, of course, it's not. I mean, I don't know, but at least that sounds part of that. That sounds like an open deformation actually, but let's stick in twist in my impression. But
just came back to deformation. So.
Yeah.
It's an example of the
yeah. So okay, so example Yamazaki deformation. Okay, yeah, and then at least for some class of series, it's a Yamazaki deformation. This is open deformation. So yes, and then so it's okay. Thank you. Yes. So then it's an open deformation. And
but on the other hand, it's also very similar to TT bar. The only difference is what are the precise operators that you're using to twist the boundary condition?
Yeah, I mean, so that's a big question. I mean, to some extent, for example, I began by saying that there is a TT bar and JD bar, etc., and I keep saying that it's misleading, etc. But I don't know. But it's true that there are some similarities actually, and it's still tempting to consider. And in fact, I mean, so as a general framework, you might think that, for example, there could be open cross duality, for example, as a statistical string set. So there is. I keep saying that there is a. I mean, but to some extent, in the end, I could integrate out the gauge, the gravity, and it's like a back reaction, and everything looks like a sort of like a open degrees of freedom. So there might be a way to formulate everything, and also. Yeah, the parallel might be still interesting, but at least yeah, it's a bit hard to say. But I have a feeling that still the cross-sector deformation is very different. So you should distinguish despite the similarity to some extent.
A sneaking last question: if you think of having, for instance, something like a string action and fixing a gauge, then before the gauge fixing, this TT bar would correspond essentially to some regular TST or regular twist, which would be like more like an open deformation. After the gauge fixing, after you essentially gauge fix the way
I see.
then it looks like a TT bar of the remaining degrees of freedom.
I see.
So I don't know if there is a relation there.
Yeah, it's probably related to how you integrate things out and then so it depends on how you integrate things out, I think. And it may look like an open or closed, for example. So yeah, I shouldn't overemphasize the difference, but for example, I mean, it does seem to affect a little bit. For example, I have an example that is, I have a story. This is the integrable quantum field theory, but you can try to discretize it to lattice and have a story of. And so in that context, for example, if you have this dynamical coordinate transmission set, or this discretization, it seems to be going, and then which is probably not unrelated to the fact that you have this non-locality coming to the field theory and things like that. So of course, non-locality might again duality frame, and there are a lot of things. So depending on how you describe it, but yeah, I think it's an interesting question overall. Like to what extent you can try to consolidate all the deformations. It seems to be very appropriate for this conference.
What?
No, go for it. Yeah, you first.
Okay. So the question probably relates to the broader context of TT bar deformation.
Yes.
Your discussion is completely general. But let's say at the end you assume you start using a particular theory, for instance, free boson or a Sugawara construction in a current algebra. How far can you get by being specializing to models of the sort I mentioned?
Well, let's see. So at least my understanding is that the dynamical coordinate transformation itself seems to be independent of the choice of the specific theory. At least
whatever you said is completely general, but
yes.
I guess at some point you are stuck or there is a certain information you can extract. But if you specialize to specific theories of interest, like West Lumino-Witten or free bosons, can you actually work?
Yeah, for example, you can follow this logic and write down the Lux, for example, and then show that and then you can, for specific theory, you can always check that it's a flat connection or not, for example. And then, well, it's not for the typical series. People already discussed that already, so it's not like we obtain new results. But at least you can do that exercise and you check one by one. For some specific, like a principal chiral model, for example, we discussed that in a paper. So you can do some consistent checks. Of course, we didn't do everything, so there are a lot of possibilities. So and then people here have exhausted a lot. So I think there's a lot of room for it. So maybe if you're not convinced, you can just try to do that similar combinations. And
after your paper.
Yeah. Thank you.
Yeah, just maybe you could clarify. I'm a little puzzled. So
okay.
So you've shown that this dynamical coordinate transformation gets the job done. It works. And you're conjecturing that the way that this would arise would be by coupling to an appropriate gravity theory and putting the graviton on shell.
Yes.
Now, what I find a bit confusing is that there are choices and varieties of TT bar type deformations. But is there the same sort of choices? I felt like the gravity you couple to is sort of uniquely defined, so its on-shell equation should be unique.
Yeah,
so I don't quite see how you get plethora of different sorts of
that's a very good point. That in fact, the short answer is I don't know. But what I would imagine is that well, there could be multiple solutions, for example, multiple classical solutions that try to solve the gravity equation, for example. And then depending on the different solutions, for example, that corresponds to different deformations, something like that. So that's what I have in mind. But if that's the case or not, I have no idea. Yeah. And yes.
But did you say you can get TT bar and root TT bar?
Yeah, that's true. That's true.
What do you do to get one to distinguish them from each other?
Well, let's see. Well, of course, there is a I mean, there is a family. So in a sense, there is a modular space of solutions in a sense. So and yeah, I mean that's how the life is. And it may look a little bit unnatural from the usual graphic perspective. Of course, it's an equation of there is no modular, but the theory is partial topological, partial or multiple set. Maybe there's some moduli space, and so the hope is that there is indeed a moduli space and analyze the dimensionality, etc., and exhaust all the integrable deformations. So that's what I have in my mind. But whether that's true or not, I have no idea. But the point is that you already know the on-shell solutions, just like one buffer. So then that does really the thing. Yes.
Yeah, maybe a related question. So, I mean, for the purposes of deformations of sigma models, there's nothing special about TT or root TT. You can deform by any function of the stress tensor whatsoever, and it preserves integrability, and all of them are realized as field-dependent metrics, just like this. So my question is, if you replaced your gamma with
Yeah.
a more general field-dependent metric,
I see.
is there any obvious obstruction? Like, would this work for?
Let's see. Yeah, I mean, probably. Yeah, I mean that's probably related with this this step where there is this. Yeah, I think there is something nice happens here, for example, and then so. I mean, if you have a yeah, I don't know.
Yeah,
but
well, I mean, I think
if you take a
replace-
general one, can you? Yeah.
I mean, my claim would be that if you replace this gamma
Yeah.
with a general field-dependent metric,
Yeah.
then the analog of the statement would be that it would be a variation of the general function of
Mm,
ft,
mm,
and you
mm,
could
mm.
always absorb that.
I see. Yeah, I mean, I see. That also sounds plausible. Yeah, I mean, we should discuss. Maybe that's true. In that case, what am I saying about the solutions, etc., might not make sense. But yeah, I mean, I don't know. Maybe there is a huge modularized space. There is a different degrees of freedom. I mean, degrees of freedom. So there are a lot of degrees of freedom. And, maybe everything goes like so. Maybe the information space might not even find a dimension. But at least it has a consequence. For example, if you just take a general function of stress tensor, etc., and if this works, that seems to me, for example, for even complicated models, like the general D model or something, probably, yeah, I mean, it may work. So you can generalize that zoo of theories, probably, and then so it has some consequence if that's the case. And yeah, and in fact, that's also a question. Like, for example, there is a complex structure deformation, etc., but it picks up a very, very particular direction, the TDR, etc. And honestly, from the 4D transform perspective, it looks very, very contrived to look at this question, that, etc. So yeah, indeed. So from that viewpoint, I have the feeling that you can go anywhere. That's the one viewpoint. But on the other hand, if you look at the literature, there's some nice thing about these deformations, and some of you can tell me more about it. So the question is like how to consolidate these different viewpoints. I think that's a big question for me.
Thank you. Last question.
Yeah, thank you very much for the nice talk. So you start from a degenerative model and you deform it, but after the deformation, you get it into a broader class of models, right? Because you are not just hitting on another degenerate E-models, but a broader class. So
Yes.
can you say something more about this broader class? And should one define E-models really in this more extended way, so to have them completed?
Yeah, I mean, probably you're asking if there's a nice characterization of that.
Exactly.
Yeah.
Because usually, you know, when you go out of a class of model and you find a broader class, it might be better to just start from this broader class.
Yeah, that's a good question. Of course, it's specified in the sense of I know what happens, etc. But the asking question is there is an invariant data you can specify or even discuss the consequences of TDRT, like
exactly, because you don't have just the double coset anymore, right? So
that's true.
You are adding in a way some additional data.
Yeah,
specifies
so probably I don't know, but probably it's like a double coset is squeezed or something, and it's not some.
But it's not, right? Because only when you just would change the double coset, it would just change the target space geometry, right?
Okay.
So, but this is not what's happening here,
that's
right?
True.
So
that's true. I mean,
deformation works differently.
Indeed. Yeah. I mean, it's yeah. Of course, it's yeah. I mean, the whole structure of the series deformed, so it's not like you're changing the geometry, but maybe the geometry itself is changed, but the whole thing, yeah. At least the structure is different, so you have a different class of series. And, yeah, I think it's interesting. I mean, maybe even just take some specific example and then how it looks like, or how does the duality. Yeah, in fact, I didn't mention too much the duality aspect of this conference, but you can try to invoke, resurrect duality. How does the T-duality happen? I think that's an extremely interesting question, and then I'm sure, so there are a lot of experts, and so I think they're happy to discuss further. Yeah.
Okay, so I think we should draw things to close. So thanks again for the nice talk.
Thank you.